listen carefully. So let's go through the proof of that. So let's do this one. So what you do is you let theta equal to cos inverse of negative x. And then what you do is you're going to write cos theta equal to negative x, like that. And then what you do is after this you can times both sides by -1, which you will get negative cos theta equal to x. And then after this, the negative, which is negative, is in the second quad. So what you do is you change that to cos pi minus theta equal to x. And then you make theta the subject. So and then you write pi minus theta equal to cos inverse of x. And then you move things to the other side. So pi minus cos inverse of x equal to theta. And then make theta the subject. So theta is pi minus cos inverse of x. And then you can, what's theta? Now theta, from our definition, is this, isn't it? So you write cos inverse of negative x, therefore cos inverse of negative x equal to pi minus cos inverse of x. So proven. Alright, so this proof needs to be known. So I'll just grab this bit, put it over at the bottom. Okay, that's theta. Okay? Alright, that's the proof. Alright, write it down. Okay, after this, then we can continue. Okay, so give you one more minute. Alright, good. Alright, let's move on to the other proof. The other proof requires you to know the complementary angle identity. So let's, it's not written on the top. Okay, so what you do is, so this one you do, let theta equal to sine inverse of x, which means sine theta equal to x, and then you go continue. Now you can change sine theta into cos theta. So you can change it to cos 90 minus theta or pi on 2 minus theta equal to cos theta equal to x. Okay? And after that, you just do the cos inverse, so pi on 2 minus theta equal to cos inverse of x. So basically, I just use the fact that cos pi on 2 minus theta equal to sine theta. Okay? And then you continue with this process, so you can, so what you do is you write minus theta equal to negative pi on 2 plus cos inverse of x, and then you times both sides by -1, and then you get theta equal to pi on 2 minus cos inverse of x. And then what's theta again? Now theta is exactly sine inverse of x. This is just this, isn't it? That's theta, which is the same theta here. I'm going to change it to here. Sine theta of x. Actually, I shouldn't have done that. Okay, good. I will continue equal to pi on 2 minus cos inverse of x. And then you just move it back to the other side. So move this thing back, so write sine inverse of x plus cos inverse of x equal to pi on 2. Yeah. Alright, so that's a proof. So so the sum of sine inverse and cos inverse is always pi on 2. Alright, good, all done. So basically you probably have seen that in the graphical way. So when you see the graph of cos inverse of x plus sine inverse of x, so probably the teacher has drawn the graph with you, so it's equal to a straight line pi on 2 from 1 to -1. So basically this is equal to pi on 2, so you have drawn the graph on page 9, okay? So now it is done algebraically in this proof here, that they add up to 90 degrees. Yeah. Okay, good. Alright. So let's see why this is the case. Why do they add up to 90 degrees? One way to understand this is from the viewpoint of the right angle triangle. So you've got sine inverse of x. So sine inverse of x is this angle here. So x1, that's the sine inverse of x, because it's opposite of the hypotenuse. And then the other one is cos inverse of x, because it's adjacent over hypotenuse. And what do we know about these two angles? They are complementary. They must add up to 90 degrees. So that's a graphical way of understanding why do they add up to 90. Because this sine inverse of x refers to this angle. Cos inverse of x with the same x refers to the other angle. They must add up to 90 degrees. Okay. All right. After we do this, then we're going to differentiate sine and cos. Okay, so all right, let's move on to differentiate sine and cos. So did the teacher go through the derivative sine inverse and cos inverse? No? Okay, let's do that. So differentiate sine, let's review this. Differentiate sine is cos. Differentiate cos, you get negative sine. And differentiate tan is equal to sec squared x. Alright, so these are the three rules that we're going to use. Let me write it again. Let's try again. Okay, so you get differentiate sine equal to cos. Differentiate cos is equal to sine equal to negative sine. And then differentiate tan, you get sec squared. Okay, good. We're going to use these rules to differentiate sine inverse. So to differentiate sine inverse, you let y equal to sine inverse of x. And then what you do is, you want to find what dy over dx is. And we can't differentiate yet, so what we do is, let's make x the subject. So sine y equal to x. And make x the subject first, x equal to sine y. And what we do is find instead dx over dy, which is equal to cos y. Okay, cos y. And then what you do is, you can flip it. You can flip, so you get dy over dx equal to 1 over cos y. And then you're going to draw a right angle triangle. In this right angle triangle, the angle is y. It's a right angle triangle, opposite over hypotenuse, right? X, because sine y is x over 1. right, opposite of the hypotenuse, and then use Pythagoras to work out the third side, 1 squared minus x squared. And then what you do is you're going to find out what cos y is. Cos y equals to adjacent of the hypotenuse, which is just this. So this thing is now replaced by 1 minus x squared, like that. Okay, good. So we proved. So that means the derivative of sine inverse is this. This is the derivative of sine inverse. The proof is not examinable, but it just shows you where the formula comes from. A very similar proof for derivative cos inverse and derivative tan inverse. You do exactly the same thing. Maybe we'll go through it as well. Let's go through the, you could try to differentiate cos inverse, but we'll just differentiate the tan inverse because it's a bit different. You could try the derivative of cos inverse by itself. You can refer to the textbook, So what we do is we're going to let y equal to tan inverse of x. And then you do tan y equal to x. And then you make x the subject, x equal to tan y. And x over dy equal to sec square y. And then if before you flip, let's draw a triangle. So in this triangle, x over 1 with the angle y, square root of 1 plus x squared. So therefore, I could find sec y in terms of x. So what you do is we're going to so cos y equal to adjacent over hypotenuse, and then therefore 1 over cos y equal to this. So you reciprocal both sides. And then what's 1 over cos y? It is sec y, isn't it? So sec y equal to 1 plus x squared, square root of 1 plus x squared, which you will substitute in here. So you can write that as square root of 1 plus x squared or square, which is equal to 1 plus x squared. That. And then now what you need to do is to reciprocal both sides, dy over dx equal to 1 over x squared. Okay, so we've got the derivative of tan inverse and the sine inverse. So that's the derivative of tan inverse, and the other one is the derivative of sine inverse. Okay, done. And then we're going to do questions on how to differentiate, and then we'll do a graph question after that. Actually, before we do that, we need to look at the derivative again. Okay, so once we finish, we're going to move on to the next page. We're going to look at this graph again and relate this to the three derivatives we just derived. Let's write them down. So if I differentiate sine inverse of x, you get 1 over 1 minus x squared. If I differentiate cos inverse of x, you will get negative. Okay? And then if you differentiate tan inverse of x, you get 1 over 1 plus x squared. Let's look at the formulas in more detail so we can relate to this. Okay, so all three are on the board. Alright, so you can see the derivative of sine inverse and cos inverse are very similar because the graphs are very similar, except one has a positive, one has a negative. The derivative tan inverse doesn't have a square root, it's 1 plus x squared instead. Alright, so let's see what it means for the, how does the derivative relate to the graph. So what you do is, we're going to Okay, let's go through this. So what I want you to do is, I want you to substitute x equal to 0 into the derivative to find the gradient at 0. So if you substitute 0, you get 1 over square root of 1 minus 0 square. And what do you get? You get 1, isn't it? So that tells you that the gradient at the origin is 1. Okay, so that tells you that. What happens if you substitute x equal to 1? And also x equal to negative 1. What would the y dash equal to? Work this out. Alright, well, you get no solution. You get 1 over, so like 1 over 0, isn't it? Which is really infinity. So we see that the gradient actually tells you that the tangent at the endpoint is vertical, right? Because it's vertical tangent. And then you will see that it's a vertical tangent as well. You get the same thing, 1 over 0. Okay, vertical tangent. Alright, like that. So you see these features are shown by the derivative, that the gradient of the graph is related to the formula. And the formula tells you that if you substitute 1, the endpoints, it gives you the vertical tangent. What else does it tell you? And you can do the same thing with cos inverse as well. So you can do the same thing, substitute x equal to 0. I think you will get negative 1 as your gradient. Okay, negative 1. Okay, so negative 1, so m equal to negative 1. And you also see that at the endpoint, the gradient is 1 over 0, which is negative 1 over 0, so it's a vertical tangent, like before, vertical tangent. Okay, vertical tangent. And then you will see that since the derivative is negative, the graph is decreasing, isn't it? Graph is decreasing because it goes down, it's decreasing. So that's how we remember the derivative. Derivative cos inverse has a negative because the graph of the cos inverse goes down. Derivative sine inverse is positive. The graph of sine inverse goes up. Okay, so that will give you an easier way to remember the derivative as well as remembering the graphs because they're related. So one goes down, one goes up. Okay, what else will we... I think that's all we can say at this point. The endpoints and in the middle, the gradient is 1. Now, of course, you can find the gradient at any point, but these are the one that's more obvious from the derivative. And the last one is the tan inverse. With the tan inverse, you see that the domain is all real x. And this is shown by the derivative, that the domain of that is all real x. Whereas this one, I can't substitute 2 in there, isn't it? Because the domain is between 1 and negative 1. So x is between 1 and negative 1. So I can't substitute 2 in here. Because if you substitute 2, you get square root of negative number. So the formula for the derivative actually shows the same restriction as the graph of the cos inverse and the graph of sine inverse. So there are restriction on the domain, which is shown by the derivative. But in this one, there's no restriction on the domain. The domain for the derivative was also all real x. What else are there? Of course, if you substitute x equal to 0, the derivative is 1 over 1 plus 0, which is 1. So the gradient at the origin is 1. Right? Now let's see what happens if you make x goes to infinity. What will happen to the derivative? It's going to go to 0, isn't it? Because you have a very big denominator, 1 over very big become very small, so derivative approaches 0, which is what we expect, isn't it? So as x goes to infinity, the y dash, the gradient, approaches 0. So because you see the tangent is getting flatter and flatter, and same thing as x goes to negative infinity, the derivative also goes to 0 as well. It gets flatter and flatter, right? Gradients approaching 0. approaching 0. Right, so we can see all these features to be shown by the derivative. And on the next page, we're going to do some question on this, how to differentiate a variety of curves using these formulas. All of these formulas are on the reference sheet, so so you know where to find them. I think that's all. Okay, let's move on to the next page then. So we're going to differentiate different graphs. Okay, good. So let's move on. So these are the 3 formulas, and we're going to use this formula to differentiate. And this one's the general version of this one, where you replace the x by f of x. So the only thing you change is where the x is, change to fx, and then you also have to times by the derivative of the fx. Okay, let's use these formulas to do them. So differentiate, the first one you have to use the product rule. So you're going to let u equal to x and v equal to tan inverse of x, like that. And then you're going to go u dash equal to 1, v dash equal to 1 over 1 plus x squared, the formula we just derived. And then you just cross multiply, and then you are going to make the screen bigger. So you're just going to get y dash is u dash v, which is 1 times tan inverse of x, plus x times 1 over 1 plus x squared. And then you're going to get tan inverse of x plus x over 1 plus tan squared. That's your final answer. All right. Okay, good. Try the next one. The next one is you don't use product rule. There's an angle here that's x squared, so you try to use this rule on the top. Okay. So what you do is you're going to write y dash equal to 1 over square root 1 minus, and you're going to square whatever's in here. So that's x squared will be squared, right? Like that. And then you also have to times by the derivative of x squared, which is 2x. That's the derivative of 2x, x squared derivative. Okay. And then if you simplify that, it's going to be 2x over 1 minus x to the power of 4. Okay, so you see how the rule works. So try the next few. Alright, try the next one. Cos inverse of 2x. So you're just using the same rule. Y dash equal to 1 over, now it's a negative for cos inverse, don't forget the negative. 1 minus something square, so you just replace the 2x, put it in here. And in addition to that, you have to times by the derivative of 2x, which is 2. Like that, and then you just have to simplify. So your answer will be negative 2 over 1 minus 4x squared. Yeah. Okay. Yep, that's on the formula sheet. I've done indirectly. So if I show you the formula sheet, it's going to be, they only give you the integral, so it's reversed, but not the derivative, but you just have to see it in reverse. So you need to memorize them. Yeah, so it's not on there. Okay, so you have to memorize. So memorize. So these ones, let's get a highlighter. And the highlighter will be, so memorize these. These are important. Not on the formula sheet. No. Okay, so let's continue. Okay, good. Alright, let's do the next one. Derivative of tan inverse. So you go 1 over 1 plus, and you square the e to the power 3x, times by the derivative of e to the power 3x is 3 e to the power 3x, like that. And then you, so that's the derivative of this diff. And then you're going to continue, so you get 3 e to the power 3x over 1 plus. Be careful with the bottom, you do e to the power 6x, because you do 2 times 3x, which is 6x, like that. Alright, 2 more to try. Have a try. Okay, good. Next one. Let's continue. Okay, let's do the next one. So the tan inverse of 1 over x. So y dash equal to 1 over 1 plus. You square the 1 over x like that. Differentiate 1 over x. How do you differentiate 1 over x? You write that as x to the power negative 1, and that will be equals to x to the power negative 1 x to the power negative 2. And then you continue, which is equal to 1 over 1 plus 1 over x squared multiplied by negative 1 over x squared, like this. And then you have to put a bracket around it, just times the x squared, times denominator with denominator, numerator with numerator, and you end up getting negative 1 on the top, and then you get x squared plus 1. Because x squared times 1 is x squared times 1 over x squared is 1. So that's your final answer. Okay, and then finally we got this angle. So you do y dash equal to 1 over square root 1 minus the square of the ratio times by the derivative of this, which is negative 1. And then you end up getting negative 1 over, you should maybe expand it, so you get 1 minus 2x plus x squared, the perfect square formula, which becomes negative 1 over 2x minus x squared. That's your final answer. Alright, I'll just enlarge the screen so you can see more of this. Alright, good. Hopefully you're finished. We're going to move on to the next derivative. Alright, so we know how to differentiate a variety of functions. Next, we're going to apply it to curve sketching. So how does that relate to this? So remember what this is? We just proved it's equal to power on 2. This is a third proof. Right? This is the third proof. So to prove that, what we do is let's find the derivative. If we differentiate that, you get negative 1 over 1 minus x squared plus the derivative of sine inverse 1 plus minus x squared. They end up cancelling. 0. So if the derivative is always 0 for all x in the domain, for all x between negative 1 and 1, therefore we say that the function must be a constant, must be a horizontal line, because the gradient is always 0. And the only way for that to happen must be a horizontal line. And the question is, what's the value of c? So to find c, you just have to substitute a random point. So let's say we substitute x equal to 0 into the function. So do y equal to cos inverse of 0 plus sine inverse of 0. This is equal to pi over 2 plus 0, which is just pi on 2. Right? And that's equal to c. So therefore, y equal to pi over 2. But remember, only between minus 1 and 1, within the valid domain, between 1 and negative 1, and the pi over 2 is over here, pi over 2. So you draw a line, so the function is this, because the gradient is always 0. So we proved that this dy dx is always 0, so it's flat. Okay, that's how we... So we prove that this is equal to pi over 2. So that's another way to prove it. Okay, and then we can use similar idea to prove, to draw other graphs. So try to do the next one by using the derivative to show that the graph is a horizontal line. First prove it's an odd function first. Now to prove it's an odd function, you just have to remember from last lesson that the tan inverse of x, negative x, is negative tan inverse of x. So that's what we proved last time on page 10, I think. Yep, page 10. So now what we do is we're going to prove this is an odd function. So what you do is you're going to let f of x equal to tan inverse of x plus tan inverse of 1 over x, and then we're going to substitute f of negative x, which is equal to tan inverse of negative x plus tan inverse of 1 over negative x, like that. And then we continue with the proof. And tan inverse of negative x is negative tan inverse of x, also negative tan inverse of 1 over x, like that, which is exactly equal to negative of fx. So we prove this is odd. Like that. And then we find the derivative after this. And then we're going to use these features to draw the graph. Okay, so find the derivative of that. So to differentiate, we'll just write down the derivative dy over dx. Derivative tan inverse, that's equal to 1 over 1 plus x squared. And derivative of this thing, we just did it before on page 13. So if you look at page 13, example 4e, we just did it, isn't it? What was the answer? Derivative of tan inverse of 1 over x. It's negative, isn't it? Alright, so we just did it from the last page. So if you look at the answer from the last page, it's equal to this, negative 1 over x squared plus 1. So we use this result. And then you will see that, like before, they cancel, become 0. So whenever derivative 0 for all x in the domain, that tells you that it must be a constant graph. It must be a horizontal line for all x in the domain. For all x in the domain. And the question is, what's the value of that constant? So whenever the derivative 0 for all x in the domain, the graph must be the function must be a constant, and the graph must be a horizontal line. And to find the value of the constant, we substitute an x value. And in this case, now we can't substitute 0 because you can't put 0 in the denominator. So I'm going to substitute x equal to 1. So we're going to substitute x equal to 1. So substitute x equal to 1 into the graph. So you get y equal to tan inverse of 1 plus tan inverse of 1 over 1. Work out what that is. Tan inverse of 1 is 45 degrees, which is pi over 4, plus pi over 4, which is equal to pi over 2. So the constant y, the constant is pi over 2. So we see they add up to pi over 2. Alright, that equal to pi over 2, like the sine inverse graph. So we draw pi over 2. Now remember, x cannot be 0. So there is a open circle here because it's not defined as 0. And then you just draw a line pi over 2. Draw a line like this. Alright, 1, 2. So unlike the sine inverse one, they go on forever. Pi over 2. But there's a problem. It doesn't just go all the way like this because it is an odd function, isn't it? Remember, it is odd. So it can't be even, odd function. So how do you make an odd function? You have to draw on the other side. You have to draw here. Then that will make an odd function. And you can check. You can actually check that if you substitute x equal to -1, that the function become negative. On a -1, so you get -pi/2. Okay? You get that at -1. Okay? So you get this feature. So basically this graph is equal to two possibilities. Is equal to 1 pi/2 if x is positive. If x is positive, or if x is negative, it's -pi/2. If x is negative. And then you see these sort of things where there's a discontinuities. So if there's a discontinuities, it's possible that they have two different constant values because there's a gap there. Whereas for the other case, there's no problem because it just have continuous graph. Okay, this one they could break here and have two different values. All right. What else I want to say? Why is it add a pi/2? This is again due to the geometry of the triangle. I can also show you why this is pi/2 as well. So if you look at the triangle, again, so you go x, so this is x over 1. So this angle is tan inverse of x. And then you will find that the other one is tan inverse of 1 over x, isn't it? And they add up to 90 as well. Okay, so that's tan inverse of x, x over 1. This is tan inverse 1 over x on this angle, and they do add up to 90 because these two angles are complementary. All right, so I think that's all we have to do. Next lesson we'll do integration, and that's it. All right, good. So today